Today we will go through the new topic, that is the ZTransform. So in the last class we have discussed about the Laplace transform. So that was for the continuous time signal. So today we will discussing the ZTransform that we use to transform the discrete time signal. So let's go through it. So in the last class we saw what is the eigenvalue and the eigenfunction. So whenever you have a system and you apply some input and you are getting the output, which is same as input multiplied by some constant. Okay. So in the case of discrete time system, this constant is actually the Z transform. Okay. So the Z transform of any signal is given as the, let's say you have a signal x of n in the time domain. In the Z domain, it will be given as x of z equal to summation n equal to minus infinity to infinity x of n z to the power minus n. Okay. Now, in the case of Laplace domain, you have the variable s, which was something like sigma plus j omega. Okay, but in the case of Z transform, we have a variable called z, which is equal to r e to the power j omega. Okay, so this Laplace domain, this s is kind of Cartesian coordinate kind of representation, but in the case of a Z transform, this is kind of polar coordinate representation. Okay. So you can think of this as a in the Laplace domain, it is a Cartesian coordinate because you have S plane where you have x-axis and y-axis, okay, sigma and j omega. In the case of Z domain, you have r, which is a magnitude, and you have omega, which is a phase or angle. Okay. So this is the polar coordinate. In the polar coordinate, if you remember from the mathematics, it is represented by r e to the power j theta. Okay, it is similar to this r e to the power j omega. Okay, so in the case of polar coordinate, uh, how do we find the point in the coordinate? So you have r, so you draw the radius or circle with radius r, and then draw the line which makes the angle theta here. Wherever they intersect, that represent the point which has the radius r and angle theta. Okay, so this is a polar coordinate representation. Now let's go to the Z transform. So let's see how do we calculate the Z transform of any discrete time system. So I have taken an example of a to the power n un. So this is which is a kind of constant and it is real number, not a complex. So this is a constant, not a variable. And here you have a time a to the power n and un. Now let's calculate the Z transform. So we have a Z transform formula which is given as n equal to minus infinity to infinity x of n z to the power minus n. Okay, and we will replace this x of n with this a to the power n un. You'll get this function. Now since you have a un here and un is equal to 0 for n equal to minus infinity till minus 1. So what we will do, we will remove this un, and instead of adding it from n equal to minus infinity to infinity, we will add it from n equal to 0 to infinity. Okay. Now this a to the power n z to the power minus n, you can also write it as a z inverse to the power n. Now if you expand this expression for n equal to 0, you will get a z inverse to the power 0, which is equal to 1. For n equal to 1, you will get a z inverse. For n equal to 2, you will get a square z to the power minus 2. And then for n equal to 3, a cube a z to the power minus 3. So if you see this series, this will continue, and this is a GP, geometric progression, where the first term is r, first term is 1, and the ratio r is equal to a z inverse. Okay, so we know that if you have a geometric progression which has an infinite term, so here we have an infinite term. Now for this kind of geometric progression to converge to a finite value, the ratio r has to be less than 1. Okay, or you can say magnitude of r has to be less than 1. Then only your GP will converge. If you have a r which is equal to or greater than 1, then what will happen that uh, if you see this number which is growing exponentially, and at n equal to infinity, you will have something like a to the power infinity z to the power minus infinity. Okay, and if you are which is a z inverse is greater than or equal to 1, what will happen that this term will become infinity. Okay. But if it is less than 1, then this will converge to 0. Okay. So because of that, we want this number to be less than 1, then only this GP will converge. Okay. So just like for the in the Laplace transform, we have the some value of the real value of the s, which makes the Laplace transform to converge to a some point. Similarly, we have a some value of the z here, which will make sure that for this range of the value of the z, this z transform is going to converge. Okay. So here R is a z inverse, and we want this a z inverse to be less than 1. So if a z inverse is less than 1, you can say that, and since this is z inverse, you can take it on this side, it will become z here. So mod of z should be greater than mod of a. Okay. And once this is converged, we know that this geometric progression will add up to 1 upon 1 minus r, where r is this ratio, a z inverse. Okay. This is the formula of the summation of the geometric progression from the mathematics I'm using it. So this is the formula of the GP. In general, it is something like this: A naught divided by 1 minus R, where A naught is the first term of the GP. But if for our case, first term is 1, so that's why it is 1 here. So once you use this formula of the GP, your Z transform will become 1 upon 1 minus A Z inverse, or you can also write it as a Z upon Z minus A. And the condition that we are getting this Z transform is that mod of Z has to be greater than mod of A. If mod of Z is less than or equal to mod of A, in that case, this GP will not converge. Okay. So this is what we call it as a region of convergence. This mod of Z is greater than mod of A. This we will call it as a region of convergence. Just like the Laplace transform, we have the region of convergence. Similarly, in the Z transform also, we have the region of convergence. Let me go to the next slide. Now, in the case of Laplace transform, we have a S plane where we have a sigma axis and j omega axis. In the case of Z transform, we have a Z plane. Okay, and here we have a polar coordinate kind of thing, not the Cartesian coordinate. So here Z is equal to R e to the power j omega. Okay, where R is R is the magnitude and j omega is the phase. Now I want to represent this mod of Z greater than mod of A in polar coordinate. How does it looks like? Okay. Now, if I write mod of Z equal to mod of A, if you remember from the mathematics, in the polar coordinate, this represents a equation of a circle. Okay, this represents the equation of a circle with radius A and center 0. Okay, so here the radius is A and its center is origin. Okay, center is 0, comma 0. Okay. Now we want mod of Z to be greater than mod of A, right? So how to find out this point? So what we will do, we will draw a circle with radius A. So this you see this the point where we have a intersection of white color and green color. That that is the circle with radius A. Okay. So this is the circle with radius A and center 0. Now whatever is outside this circle, that is represented by this equation. Okay, so whatever is outside this circle, which I have highlighted in the green shade, that is mod of Z is greater than A. So all the point is covered by this equation. Okay, so our Z transform is going to converge in this green point, but it is not going to converge inside this circle or on this circle. Okay, so inside this circle, mod of Z will be less than mod of A, and on this circle, just at the circle, mod of Z will be equal to mod of A, and outside this circle, mod of Z will be greater than mod of A. Okay, so only at the outside this circle, this Z transform is going to converge. Yeah, I've just given one example, like a few other things. So if your A is the value a that you see here, if it is greater than 1, and then it is how it is going to look like. You will have a circle with radius 1, and since a is greater than 1, this circle will be outside this circle. Okay, and if you have a circle with radius 1 and a is less than 1, then your circle with radius a will be inside this z equal to 1 circle. Okay, this we will see what is the significance of this two thing. Okay, this we will see later when we study about the system in the z domain. Go to the next slide. Now let me take one more example. So here I have taken minus a to the power n u minus n minus 1. Now if we try to calculate the z transform of this signal, okay, so this is the signal. Okay, I have replaced xn with this signal and the z to the power minus n. Now since it is u minus n minus 1, you can change this summation sign. Instead of minus infinity to infinity, you can add it from minus infinity to minus 1. Okay, over this range, this u minus n minus 1 will be equal to 1. For rest of the value, it will be equal to 0. Now again, if you see this, you can write it like this as well. And here at the power you have minus n, and here n is varying from minus infinity to minus 1. So what you can do, you can exchange this sign with the limit sign. Okay, so you can make it n, instead of n you can make it plus n, instead of minus n you can make it plus n, and instead of minus infinity you can make it infinity, and instead of minus 1 you can make it 1. Okay, it will not make any difference. Okay, now if you see this again, this expression, this is a GP. Okay, if you expand this from n equal to 1 to infinity, this is again a GP. And in this case, when you expand this, this is the kind of thing you are going to get. There is a minus sign at the outside. Then first term will be a inverse z. Second term will be a to the power minus 2 z square. Then a to the power minus 3 z cube, and so on. It will continue. Now, this is the first term. That is our n naught. Sorry, a naught divided by 1 minus r. This is the formula for the summation of the GP. So a naught is a inverse z, and r will be equal to a inverse z. Okay, so once you put it in this formula, this is what you are going to get. Okay, a naught divided by 1 minus r. Now again, for this GP to converge, we want this r to be less than 1, or the magnitude of this r to be less than 1. So magnitude of a inverse z should be less than 1, or magnitude of z should be less than magnitude of a. Okay, so in this case, the region of convergence is mod of z should be less than mod of a. Now, if you see this z transform, this z transform is same as the z transform that we derived in the last slide. But the thing is that here the ROC is different. In the last slide, ROC was something like mod of z greater than mod of a. In this case, the ROC is mod of z less than mod of a, just opposite case. Okay, so in this case, to find out the region of convergence in the coordinate, you need to just plot a circle with radius a, and whatever point is there inside this circle, on those point, this z transform is going to converge. Okay? So in this case, the region of convergence is mod of z less than mod of a. To go to the next slide. Now I have taken one question from one of the ES problem. So here we have a signal which is given as 1 of by 2 to the power n un, and we have another signal minus 1 by 3 to the power n un, and we need to find out what will be the ROC of this signal x of n. Okay, so first term is 1 by 2 to the power n un. Okay, so we are going to use a formula that we just saw, that is, if you have a to the power n un, the z transform of this signal will be equal to 1 upon 1 minus a z inverse, and the ROC will be equal to mod of z greater than mod of a. Okay, so if you take this and calculate the z transform of this signal, it is going out to be 1 upon 1 minus 1 by 2 z inverse. Here the difference between this and this is that a is replaced by 1 by 2. That's all. So I have replaced this a with 1 by 2 here, and the ROC will be equal to mod of z greater than 1 by 2. I'm not putting mod here across 1 by 2 because 1 by 2 is already a real and positive number. Now the second term is minus 1 by 3 to the power n un. Okay, again I will be using the same formula. So the Z transform for this signal will be 1 upon 1 minus a, where a is equal to minus 1 by 3 Z inverse. Okay, and ROC will be equal to mod of Z greater than mod of minus 1 by 3. Okay, or you can say that mod of Z greater than 1 by 3. So this Z transform will be 1 plus 1 by 3 Z inverse. Okay, now we have calculated the Z transform of this individual signal. So when you combine them, Z transform will be equal to this plus this, and your ROC will be intersection of this and this, because for the overall signal we have to find the ROC, not the individual signal. We have to find the ROC for the complete X of n, and ROC should be such that it satisfies this case as well as this case. Okay, that's why we need to find out the intersection. Now you have mod of Z greater than 1 by 2 and you have mod of Z greater than 1 by 3. Okay, so if you see the intersection, so let me just write here like this. So let's say that this is Z here and it is 0 and it's going till infinity, and we have 1 by 3 here and 1 by 2 here. We know that 1 by 3 is less than 1 by 2. That's why 1 by 3 is coming before and 1 by 2 is coming after. Now for the first signal, ROC is from 1 by 2 to infinity. And for the second case, ROC is from 1 by 3 to infinity. And if you take the intersection of this two, you see only this region is overlapping. Okay, from 1 by 2 to infinity. Okay, 1 by 3 to 1 by 2, there is no overlap because this thing is not there. Okay, so when you take the overlap or intersection of this two, you will get mod of Z greater than 1 by 2. Okay, so this will be the answer, which is this one. Okay, now here, what is the mistake that people make here is that because there is a minus sign here, but there is no minus sign here, right? But they get confused and think of this as a signal, which is something like this: a to the power minus a to the power n u minus n minus 1. Okay, and use the Z transform of this one to calculate the Z transform of this, and then the result will be wrong. Okay, with that you will not be getting the correct answer. So don't get confused with this. For this case, u has to be minus n minus 1, but in here we have un, not u minus n minus 1. To go to the next slide. Okay, now the similar to the Laplace transform, in the Z transform also we have a poles and zeros. So let's say we have a case where we have a Z transform which is equal to Z into Z minus 3 by 2 and Z minus 1 by 3 and Z minus 1 by 2. Okay. So again, similar to the Laplace transform, where you take the numerator polynomial and equate it to 0 to find out the root of the numerator polynomial, and that will give you the zeros of the x of z. So in this case, zeros will be z equal to 0 and z equal to 3 by 2. Okay. Now to find out the pole, you take the denominator polynomial and equate it to 0 to find out the root. That will be the pole. So z minus 1 by 3 and z minus 1 by 2 equated to 0. The root will be 1 by 3 and 1 by 2. So these two are the poles of the Z transform. Now, if you try to put this pole and 0 in the Z plane, this is how it is going to look like. You have one 0 at Z equal to 0, which is here. You have one 0 at Z equal to 3 by 2, which is here. You have one pole at Z equal to 1 by 3, and you have one pole at Z equal to 1 by 2. Okay. So this is how we represent the pole and 0 in the Z plane. Now let's see the property of the ROC. So the first property is same as what we have seen in the Laplace, that ROC should not contain any pole. In the Laplace domain also, ROC was not containing any poles. Now the second thing is, if you have a signal which is a finite duration signal, then your ROC will be entire Z plane. There may be a chance that you have to remove the Z equal to 0 or Z equal to infinity point for it to converge. Otherwise, most of the cases it will be entire Z plane, except some cases Z equal to 0 you have to remove, or Z equal to infinity, or maybe both. So I will give you guys all three examples. So let's say we have a signal which is a xn equal to delta n. Okay, this is an impulse. So if you plot it, this is how it is going to look like. It is just a one value at n equal to 0. Okay, this is our delta n. Now if you take the Z transform of this signal, which is something like, so Z transform formula is like this. Okay, n equal to minus infinity to infinity. Now this signal exists only at n equal to 0. So you will put just n equal to 0. So it will be x of 0, z equals 0. And x of 0 is equal to 1 because it is impulse, unit impulse. So it will be 1. Okay. So the Z transform of this impulse is equal to 1. And here you are not taking any help on the Z for to make it converge. It means that in this case, the ROC will be entire Z plane. Okay. For all the value of the Z, this Z transform is going to converge. Now let me take the second case where in your signal is del n minus 1. Okay, in this case again it is a impulse, unit impulse, but it is shifted version of that. So it will be located at n equal to 1. Okay, at n equal to 1. Now if you, for this case if you calculate the Z transform, so again you will be using this formula. Now in this case only for n equal to 1 we have a signal. So you will be putting n equal to 1 here, and you will get x of 1 z to the power minus 1, and x of 1 is equal to 1 and z to the power minus 1, or you can say simply z to the power minus 1. Now if you see this term, you can also write it as a 1 by z. Okay, this 1 by z will converge only when z is not equal to 0. Okay, for rest of the value of the z, this 1 by z is going to converge, but as soon as you put z equal to 0, this is going to become infinity. Okay, that's why for this case ROC will be entire as plane except at z equal to 0. Okay, so you see you have this two finite duration signal, but for first case the ROC is entire z plane, but for the second case ROC is entire z plane except at z equal to 0. Okay, now let's check the third case where your impulse is located at n equal to minus 1. Okay, in the first case it was n equal to 0, second case n equal to 1, third case I have taken n equal to minus 1. So if this case you calculate the Z transform, your Z transform will be equal to Z. Okay, because here it is located at n equal to minus 1. So once you replace this n with minus 1, you will get just Z here. Okay, so your ROC is Z, and since this is just a Z, and when you put Z equal to infinity here, this x of Z is going to be infinity, and at that point it is not converging. That means that ROC is again the entire S plane, sorry, entire Z plane except at Z equal to infinity. So similarly, for any finite duration signal, you can check that whether like what kind of signal you have, and you can find out which of the point you have to remove, or you have to either you have to keep the entire Z plane or entire Z plane except at Z equal to 0 or Z equal to infinity if it is a finite duration signal. Anyone has any doubt? Go to the next slide then. Now, third property is same as what we have seen in the Laplace property. So if you have a right-sided signal, okay, let's say you have a signal which is xn is equal to un, which is a right-sided signal. In that case, ROC will be in this form, mod of z greater than r naught. Okay, so in this case, ROC will be in this form. Now, for example, if you remember the signal x of n is equal to e to the power n un. If you take the Z transform of this, it will be a 1 upon 1 minus a Z inverse, and ROC will be mod of Z greater than mod of a. Okay. Now, I am just replacing A with 1 here, then it will simply be UN. So the Z transform will be 1 upon 1 minus Z inverse, or you can also write it as Z upon Z minus 1. Okay, and ROC will be greater than mod of Z greater than 1 because A is equal to 1. So this is one of the example. You have right-sided signal and ROC will be in this form, mod of Z greater than some number, and this number is generally the largest pole you have in the X of Z. In this case, we have only one pole, okay, which is Z equal to 1. So your ROC will start at that point. So this is the point where you have the pole, and ROC, you draw the circle around this pole, which is the largest pole here, and ROC will be all the point outside this circle. Okay. So in the case of Laplace domain, it was kind of you draw the vertical line and all the point right side of the vertical line is a part of the ROC. In this case, you draw a circle, and the circle will be located at the largest pole. In this case, we have only one pole, which is at Z equal to 1, and the ROC will be outside this circle. So this is the property which is very similar to what we have seen in the Laplace. Anyone has any doubt in this? Let me go to the next slide. Next is if the signal is a left-sided signal. Okay, so if the signal is left-sided signal, so I've taken this example. So the Laplace, Z transform of the signal will be 1 upon 1 minus Z inverse, or Z upon Z minus 1, and ROC will be something like this. So whenever you have a left-sided sequence or signal, ROC will be in this form: mod of Z less than R naught, where R naught is the smallest pole. Okay, the smallest magnitude pole. And in this case, we have only one pole, which is at Z equal to 1. Okay, so you draw a circle at Z equal to 1, and whatever the point that is inside the circle, those point will be the part of the ROC. Okay. So for right-sided signal, ROC will be in the form of mod of Z greater than R naught, but for the left-sided signal, ROC will be in the form of mod of Z less than R naught. Let me go to the next slide. Now, if you have a signal which is a two-sided signal, okay. So in the case of Laplace transform, for the two-sided signal, ROC was kind of something like this. You draw two line, okay, you draw two line, and ROC will be something like stripped between these two vertical line. In the case of Z transform, it is very similar. You draw two circle here instead of two line. You draw two circle, and ROC will be stripped inside this two circle. Okay, so it will be in this form: greater than some number but less than some number. So when you draw this R naught is the inner circle and R1 is the outer circle. So one example is xn is equal
In
to yeah.
hello,
Yeah.
sir, in last question, actually one minus sign will be also there, na, in the X of Z part.
Yeah, here there is a minus sign. Yeah, there will be minus sign here.
Okay, okay. Thank you, sir.
Yeah. Okay. So for this one, xn equal to b to the power mod of n. Let's say we want to calculate the Z transform. So here we have mod of n. So what I will do, I will divide this into two parts. One is n greater than or equal to 0, one n less than 0. And I will use the mod property. So x of n, you can write it as a, for the positive part, you can simply write it as a b to the power n un for n equal to or greater than 0. Second part, you can write it like this: b to the power minus n u of minus n minus 1. Okay. So we have a two signal here: b to the power n un, b to the power minus n u minus n minus 1. Okay. I will not calculate the exact Z transform. I will just check the ROC. Okay. For this signal, ROC will be something like this: mod of Z greater than P, right? For this signal, this signal you can also write it as a 1 by B, sorry, yeah, 1 by B to the power n u minus n minus 1. Okay. So for any signal which is something like this, a to the power n, u minus n minus 1, we saw that ROC will be in the form of mod of z less than mod of a. Okay. In this case, ROC will be in the form of mod of z less than 1 by b. Okay, where a is same as 1 by b here. So first one is giving me mod of z greater than b. Second one is giving me mod of z less than 1 by b. So when you write the overall, it will be, so mod of z greater than 1 by b, sorry, mod of z greater than b and less than 1 by b. Okay, and b is less than 1 but greater than 0. So it means that 1 by b will be greater than 1, greater than b, because b is less than 1. Okay. So now if you try to represent in the z plane, you first draw a circle with radius 1 by b, which is outer circle. Draw a circle with radius b, which is inner circle, and all the point inside this circle will be the ROC. So for the two-sided signal, ROC will always be in this form. Okay. So all this property that we saw for the Z transform is very similar to what we have seen in the Laplace transform. Anyone has any doubt here? Okay. Now, one more thing here is that if here I have taken this criteria that b has to be less than 1 but greater than 0. But let's say you are taking a case where b is greater than 1. Okay. When b is greater than 1, okay, when you calculate the Z transform, again you will follow the same sequence, whatever I have done. For this, for the first one, you will get mod of Z greater than b. For the second case, you will get mod of Z less than 1 by b. And finally, your ROC will be in this form. But if you see this expression for the Z greater than 1, what will happen that? So if you look at this expression for model for b greater than 1, what will happen that this term will be less than this one. Okay, so if b is greater than 1, then b will be greater than 1 by b, right? But by looking at this expression, it is other way around. 1 by b has to be greater than 1 by b, which is not true if b is greater than 1. And that's why we don't have any point where the Z transform of this signal will exist. Okay, it is same signal as this one, but criteria is that b is greater than 1 here. So for the same signal, if b is greater than 1, we cannot calculate the Z transform. Okay, because there is no arrow point on the Z plane for which this Z transform is going to converge. Anyone has any doubt? Okay, let me go to the next slide then. Now let's go to the property of the Z transform. So it is very similar, again very similar to what we have seen in the Laplace. So first is the linearity. You have a two signal. First signal has x1z as a Z transform. Second signal has x2z. And if you do the linear combination of this time domain signal, Z domain signal will also be the linear combination, same linear combination. Okay. Second property is the time shifting. So when you do the time shifting in the time domain, in the Z domain, you will be multiplying it with z to the power minus n naught. Okay. Next is the scaling in the Z domain. So let's say you have a signal x of z, and here you are scaling in Z domain. Okay. Instead of Z, you are replacing it with Z by a. That's what we call it as a scaling in Z domain. So in the time domain, you will be multiplying it with a to the power n. Okay. So this is the property that you can look through this also, this example also. So you have un and its Z transform is 1 upon 1 minus Z inverse. Okay. Now for a to the power n un, Z transform is 1 upon 1 minus a Z inverse. Okay. So you see, you can also write it as a Z upon Z minus 1. Okay. Now, once you go from here to here in the time domain, in the z domain, you will be replacing z with z by a. So you will be writing it z by a minus 1. Or you can also write it as z upon z minus a. Or you can write it like this also. Okay. So when you do the scaling in z domain, in the time domain, you will be multiplying it with a to the power n. Next is the time reversal. So when you have a signal x of n and its z transform is x of z, then if you do the time reversal, the z transform will be equal to x of 1 by z. Okay? And ROC will also get reversed. So one example is if you have, let's say, I think that example we have not seen. So if you have a u of n, its z transform is z upon z minus 1. ROC is mod of z greater than 1. If you take the u of minus n, okay, its z transform, you have to just replace z with 1 by z. So 1 by z, 1 by z minus 1, and mod of z will be less than 1. Okay, so r became 1 by r. That means that mod of z, here it was mod of z greater than 1. Here it will become mod of z less than 1. Okay, and z you have to replace with 1 by z. So it will become 1 upon 1 minus z. Okay, so this will be the z transform for this u minus 1, u minus n.
Can I see the last slide once more? That
Yeah.
before that,
Before this or this one?
before this.
Okay.
Linearity and time. Okay. Thank you, sir. Thank you.
That's fine. Okay. Now we have a question that is like loosely based on the the time inversion property. So let's say you have a signal which is satisfying this criteria that x of n is equal to x of minus n. Okay, and we have x of z, which is a z transform of the x of n, and this x of z has a 0 which is located at 0.5 plus j 0.25. Okay, now here which of the following must be also a 0 of the x of z. Okay, so by looking at the question, it's very difficult to gauge. So you have to use the time reversal property here. So for x of n, you have x of z, and x of minus n, you have x of 1 by z. But here our case, these two are same. It means that these two also be same, right? So it means that x of z should be equal to x of 1 by z. Okay. Now if you write x of z, let's say it is something like this. Since it has 0 here, so it will be like z minus 0.5 minus 0.25j. Okay, this is a 0. And let's say there are some other term also. I'm just writing it as a some, let's say k. And in denominator, it has d of z. We don't know what is all this number, but let's just write it. Now, let's see, we have x 1 by z. So when you replace z with 1 by z, you will be replacing this z with 1 by z minus 0.5 minus 0.25j. Okay, this also you will be replacing with this, and denominator also you will be replacing with that. Okay, now if you take this numerator and calculate the root to find out the 0, you will see that in this case it is something like this. So 1 by z minus 0.5 minus 0.25j is equal to 0. Okay, or you can write it as a 1 by z is equal to 0.5 plus 0.25j, or you can say that z is equal to 1 by 0.5 plus 0.25j. Okay, so you have a 0, this number here, it is just inverse of that. So whenever you have a signal which is satisfying this property, or you can say the even signal, it will have a two pair of 0. If it has 0 at this location, then it will have 0 at this location also. Okay, so this will be the correct answer. Anyone has any doubt here?
Can you explain again, sir?
Okay. Okay, so let me assume that we have a signal which is satisfying this criteria. It has 0 at, let's say, z equal to a. Okay, I'm not talking about now this number. Let's say it is some general number. Let's say z equal to a. Okay, and it is satisfying this criteria. Now, if you write the x of z, you can write it like this. Since it has 0 at a, you can write it that it in the numerator you have a term z minus a, and let's say some other term k of z divided by d of z. We don't know about this two polynomial k of z, d of z, and we also don't care about that. We just care about this z minus a. Now we know that this term is also same as x of 1 by z. Okay. Now if this is the x of z, what will be the x of 1 by z? You just replace this z with 1 by z. So it will become 1 by z minus a k of z, sorry, k of 1 by z, and then d of 1 by z. Okay. Now to find out the root of this x of 1 by z, to find out the 0 of this x of 1 by z, you take the numerator and equate it to 0. Okay, so in the numerator we have 1 by z minus a, and I will equate it to 0. So I will get 1 by z is equal to a, or z is equal to 1 by a. Okay, now this is the root of, this is the 0 of x of 1 by z, and since x of z and x of 1 by z are same, these two are same, it means that this 0 should also be the 0 of this one. Okay, so if you have any 0 at z equal to a, and it is satisfying this criteria that x of n is equal to x of minus 1, then it should have another 0 at z equal to 1 by a. Okay, now based on this, if you have a 0 at 0.5 plus j 0.25, you should have a 0 at just just take the inversion of this, and that should be the another 0. Now is it clear?
Yes, sir.
Yeah.
Sir, when we take the Z transform of x of minus n, in that case, why the ROC will become less than of that roots actually? In the last slide, you have said that.
Okay, if you take this thing, right, u of minus n. Okay,
Yes, sir.
so when you calculate the Z transform of this, so it
Mm.
is going to be something like this: n equal to minus infinity to infinity, u of minus n, z to the power minus n. Now since this is u of minus n, instead of summing it from minus infinity to infinity, I will sum it from minus infinity to 0,
0, yes, sir.
z to the power minus n. I will remove this because now there is no significance of this. Now if you expand this, you'll get for n equal to 0, you'll get 1. For n equal to minus 1, you'll get z, z square, z cube, and so on, right? Here
Yes,
all
sir.
n are negative. Because of that, you are getting positive power. Okay. Now this is again a GP, and if you do the GP, we want it to converge, and we know that to make it converge, R should be less than 1, and in this case, R is Z, right? Just a Z,
Z, yes, sir.
correct? So Z should be less than 1 here, or you can say mod of Z should be less than 1. Okay, that is
Okay.
this. Yeah. So whenever
Yes,
you do
sir.
the time reversal, it just become the ROC just changes its this inequality. If it is greater, then it will become less than.
Okay, so means, sir, for the both-sided signal, we generally get some ring kind of ROC. So in that case, also equality just change. The value of the roots also change, no, sir? In that
No,
case.
in that kind of cases, okay. So if you have a both-sided signal and you're changing the sign, right?
Yes, sir.
So let's say you have ROC something like this, some number A and less than some number B. Okay. Now you're changing the sign, and your ROC is getting reverse. Okay, it has now become greater than B and greater than A. Now if you see these two are contradictory because here B is greater than A, here A is greater than B. Okay.
Yes, sir.
So
Yes.
for the two-sided signal, whenever you take the time reversal, if for one case Z transform may exist, for other case Z transform will not exist. Because
Okay.
here we don't have any point for which Z transform is going to converge.
That, yes, yes. ROC will not exist in the second case, no, sir?
Yes, yes. Yeah.
Okay, okay. Thank you, sir.
Any other doubt? Then let me continue. Okay, this property I forgot to tell you in the Laplace, so I have covered here also. So what it is a conjugation property. So let's say you have a signal x of n and its Z transform is x of z. Then if you take the conjugate of the signal, which is x conjugate n, then the Z transform will be x conjugate z conjugate. Okay, ROC is not going to change. Now if your signal x of n is a real signal, so we know that if signal xn is a real, if you take the conjugate, it doesn't matter. It will be still be the same because it doesn't have any imaginary term. Okay, so in that case, the x of z will be same as x of conjugate and z conjugate. Okay. Now, what is the implication of this? So whenever you have a real signal x of n, okay, and let's say its z transform is x of z. Okay, so let me take example. Let's say we have x of z, and let's say it has a 0 which is located at a minus jb. Okay, so this is x of z, and let's say there are some other term also, but I don't care about those. I'm just taking one example here. Now this should be same as x of conjugate of z conjugate. Okay, what it means is that if you take this, okay, take this x of z and take the z conjugate and complete conjugate both. So this is how it is going to look like. So in numerator also you'll do those operation, denominator also you'll do some operation, but I will be focusing on this term. So it will be z conjugate. Okay. Now since I'm taking conjugate, your imaginary term will change its sign. Correct? Something like this. Now we know that this and this has to be same for the real signal. Why? Because x of n and x of conjugate n are same. Now because of that, what will happen that this term and this term, okay, should exist simultaneously for the z transform of x of z. What it means is that if you have any pole located at a plus jb, then there should be one more pole located at a minus jb. Okay, if signal is real. So it means that whenever the signal is real, then the poles should be in conjugate form. What it means is that if you have this one, then you should have this one also. Okay. Similarly, for the 0 also, if you have a 0 located at a, let's say c plus jd, then there should be a 0 at c minus jd also if xn is a real signal. Okay. So for any real signal, the pole and zeros are if poles and zeros are complex, they will be in form of conjugate. Okay, there should not be the case that you have this pole but you don't have this pole. Okay, if this is the case that you have this pole but you don't have this pole, in that case this xn will become complex signal, not a real signal. Okay, so for all the real signal, the pole and zeros, if they are complex, they should be in the form of conjugate. Okay. Is this point clear? Okay. So similarly, for the continuous time signal, when you take the Laplace transform, you have the same property here. Whenever the signal xt is a real, then in that case, its poles and zeros, if its poles and zeros are complex, then it should be in the form of complex conjugate. Okay. Anyone has any doubt? Let me go to the next slide then.
Sir, where is actually these these signals used?
No, complex signal are kind of not realizable signal in real time, in real scenario. It's just for the mathematical purpose we use it. Okay. In the time domain, it's not there, but in the frequency domain, we have the complex. So whenever you have a time domain signal, when you take the its ZTransform, we will see later on Fourier transform and Fourier series and all those. So when you take the Fourier transform in the frequency domain, you'll see some complex signal. Those kind of signal exist in the frequency domain.
Okay.
Next is the convolution property. So it is same as what we have seen in the Laplace. So when you do the convolution of the two signal in the Z domain, it will become multiplication. Okay. So it's very so this property we will again see when we discuss about the discrete time system, because this property is very useful for the discrete time. I mean, not just discrete time, continuous time system also. This convolution property is useful. Now differentiation in Z domain. So when you take the signal and differentiate in Z domain, you will get n into x of n, but there is a minus Z term also here. Okay, you have to be careful with this, and ROC is not going to change here. And next is the accumulation property. So this is very similar to integration property of the Laplace transform. So when you have a signal x of n, its Z transform is x of z. When you apply the accumulation property in the Z domain, you will be dividing it by 1 minus Z inverse. Okay. In the case of Laplace, you divide it by s, right? X of s divided by s when you do the integration in the time domain. In the Z domain, you will be dividing it with 1 minus Z inverse. Let me go to the next slide. Okay. So I have taken this problem from the gate. So let's say you have a this gate time signal x of n and y of n, and they are related by this formula. Okay. Now the Z transform of the y of n is this. Then what is the value of x of 2? Okay. So to find out the value of x of 2, we need to find out what is the x of n first. Okay. So to find out x of n, you need to know what is x of z, because everything here is in Z domain as of now. Okay. Now here, if you see this thing, here we can use the accumulation property. So when you take this expression and take the Z transform on both sides, it will be equal to y of z, and on the right side you'll get x of z divided by 1 minus z inverse. Correct? So this is the accumulation property I have used. Now y of z is here, it is given, and it is equal to 2 by z minus 1 square. Okay. Now this one you can also write it as a x of z into z divided by z minus 1, which is equal to 2 divided by z minus 1 square. So this you can cancel out with this, and you will get x of z, which is equal to 2 divided by z square z minus 1. Okay. Now this is the x of z. This x of z you can also write it as a 2 into z to the power minus 3 into z upon z minus 1. Okay, you can write it like this. So there is a multiplication here. If you see these two are same, I have just written it because I am going to use some property here. Now for this signal, we know what is the x of n. So for this signal, it is u of n. Correct? Now if in z domain, when you multiply any signal with something z to the power minus some number, in the time domain you are going to shift it. Okay, so in this case, when you multiply it with z to the power minus 3, you're going to shift it. Okay, so for z upon z minus 1, in the time domain it is u of n. When you take the z upon z minus 1 and multiply it with z to the power minus 3, in the time domain it will become u n minus 3. Okay, and then you have a multiplication by 2 here. I will multiply it by 2 and I will multiply it by 2 here. Okay, so this is the final signal, which is x of n. Now we need to find out what is the x of 2. So when you plot this, it will be, this is a unit step but delayed version of it. So when you plot it, it is going to start at n equal to 3. Okay, and you have been asked to find out value of x of 2. So this is 0, n equal to 0, this is n equal to 1, this is n equal to 2, this is n equal to 3. So x of 2 will be equal to 0. So here you have to use that. If you don't know the accumulation property, then this problem will become very difficult to solve. Anyone has any doubt? Okay. We go to the next slide then. Okay, this is a very interesting problem. So we have a signal x of n.
Z minus 1. Hello.
What?
Sir, so 2 upon z square into z minus 1. So you can also write 2 minus 2 into z to the power minus 2 into 1 minus z to the power minus 1 in this form also, na sir?
Oh, wait. What you mean is that we can write it to z to the power minus 2, z minus 1 to the power minus 1.
Yes, sir. Then
Yeah.
taking out minus and common and then expanding.
Yeah, that you can do if you are able to expand it. Like if you know the series, binomial series, you can write it and then find out
Yes,
the
sir.
x of 2. Yeah.
Yes, sir. In that case, z to the power minus 2 term is exist. So x equal to 2 value will come
No.
in actually.
So when you are expanding it, you have to be careful about how, like whether you are expanding in the left sided. There are two kind of expansion, right? There
Yes, sir.
are
Yes.
left-sided expansion, and that we'll discuss in the, I think after few slides, so it will be clear.
Okay, okay, sir.
So yeah, so you can expand it in two ways. One expand is just expand here itself, and one way is to make it in this form and then expand it. Correct? Take the z out,
It's,
and this, it will be this form, and then expand it. With that, you will get a different answer.
okay,
Right?
okay, sir.
Yeah.
Okay.
So we have a so in this problem we have a sequence x of n, which is equal to 0.5 to the power n u of n. Okay, and here we are convolving this signal with itself. Okay, we are doing the convolution of xn with itself and finding a new signal y of n, and we need to find out what is the summation of this thing. Okay, so here if you go to the direct calculation of this y of n and then do the summation sign, it is going to be pretty lengthy. Here you have to use very interesting thing here. So when you have a x of z, okay, so you can write it like this: x of 0 plus x of 1 z inverse plus x of 2 z to the power minus 2, and so on. And similarly on the negative side, you can write x of minus 1 z plus x of minus 2 z square, and so on. Okay, when you make this z equal to 1, what will happen that essentially you are adding all the x of n. Okay, you will be adding this. So this capital X of 1, you can also write it as a summation n equal to minus infinity to infinity x of n. Correct? So this is the property that we are going to use. Okay, but here we don't need to apply it on x, we need to see it on y. So first we need to find out what is the y of z. Okay, so y of z will be equal to x square z. Okay, because in the time domain they are convolution, in the frequency domain it will become multiplication. Now what is the x of z? So we'll use the formula that we have seen few slides back, 1 upon 1 minus 0.5 z inverse. Okay, this is the x of z. So y of z will be equal to 1 upon 1 minus 0.5 z inverse square. Okay, so this is the y of z. Now to find out summation of y n equal to minus infinity to infinity y of n. Okay, what I have to do, we have to just replace this in this y of z equal to with z equal to 1, and then this whatever the number on the right side you will get, that will be the summation of this. Okay, so once you replace this z equal to 1, you'll get this, or you can say 0.5 square, or you can say 4. So by using this kind of property, you can very easily calculate what will be the summation of yn. Anyone has any doubt? Let me go to the next slide then. Next is the initial value theorem and the final value theorem. So again, just like the Laplace case, the initial value theorem you should use only for the causal sequence. Okay, what it means is that there should not be any value for n less than 0. Okay, for this kind of signal, x of 0 will be given as limit z tending to infinity x of z. Okay, so if you see the x of z, if it is causal signal, it will start from x of 0, then x of 1, z inverse, x of 2, z to the power minus 2, and so on. And once you put z tending to infinity in this expression, all the term will become 0. This term, all those terms, except this one. Okay, so once you put z tending to infinity, that will give you the x of 0. Now, why we are talking it has to be causal, because once it is non-causal, it will have a term like x of minus 1 into z, x of minus 2 into z square, and if you put z tending to infinity in this kind of term, you will get infinity, and that will not give you the correct result. Okay, so to apply this initial value theorem, signal has to be a causal signal. Next is the final value theorem. So again, we will apply it for only for the causal signal. So in this case, the x of infinity is given as limit z tending to 1, 1 minus z inverse x of z. Okay. So in this case, if you see this, you have a x of z minus x of z, z inverse. Okay. Now, as I told, I think in the last slide itself, when you put z equal to 1, what you are calculating is summation of all the x, right? Summation of xn. Okay. In this case also you will be in this case you will be calculating the summation of x of n. In this case you will be calculating the summation of x of n, which is delayed by n equal to 1. Okay. So in the first case you will be adding x of 0 with x of 1 with x of 2 and so on till x of infinity. In the second case you will be adding like, so it is now delayed. So okay, this one minus 1. So there will be x of minus 1, not delayed actually, it is advanced. Okay, like this, and it will again go. Now, when you subtract this 2, this second signal is kind of left shifted. Okay, so this will cancel out this will cancel out this will cancel out this, and this term will be equal to 0 because it is a causal signal. So for negative value of time, there will not be any signal. So this cancellation will continue, except for this x of infinity. Rest of them, they will cancel out each other, right? Because they are kind of, since this second signal is shifted, okay, the last signal will not get cancelled out, and that's why once you apply this formula, you'll get x of infinity. Let me go to the next slide. So this problem is based on the final value theorem. So one more thing I forgot to mention, that in the final value theorem, you should apply only when all the poles are outside the z equal to 1 circle. Sorry, inside the z equal to 1 circle, or at max only one pole at z equal to 1 circle. Okay, if there are more than one pole at z equal to 1 circle, you should not apply. Okay, so either all the pole has to be inside this, or if there is a one pole at z equal to 1, that is also fine. But there is more than one pole at z equal to 1, that is not fine. And if any of the pole is outside the z equal to 1 circle, this final value theorem you should not apply.
Sir, how can we understand that?
No. So if problem is given, you need to check the location of the pole, whether they are inside or on the z equal to 1 circle or outside.
Sir, I was just asking that. How do we know whether this final value theorem gets applied, whether it's inside or outside?
Okay. So it is same as Laplace. So in the Laplace also, I discussed that whenever the pole is at the right half of the S-plane, what happens that when you put this final value theorem, it becomes infinity, right? If you remember from the Laplace. So in the Laplace, I gave you one example of this one. Okay, let me give you example here. So let's say, okay, let's say you have a case a to the power n un, okay, and its Z transform is 1 upon 1 minus a Z inverse. Okay, and here in this case, let's assume that a is greater than 1. Okay, a is greater than 1. So if you calculate the pole, what will be the pole location? 1 minus a Z inverse equal to 0, 1 equal to a Z inverse, or Z is equal to a. Okay, your pole is equal to a and a is greater than 1. It means that your pole is outside the Z equal to 1 circle. Okay, your Z equal to 1 circle is here and your pole is somewhere here. Okay, now here a is greater than 1. Now if you see this expression and find out what will be the value of this x of n at n equal to infinity, it will come out to be infinity. Okay, but if you take this expression and put it into the final value theorem, you'll not get infinity. Okay, you'll get some finite number. Okay. Actually, you will get sometime you'll get some finite number, and sometime you'll get kind of infinity by infinity or 0 by 0 kind of term. Okay. Z upon Z minus 1. Now, yeah, wait. Yeah, now you can apply actually in this case you are getting infinity here, but yeah, some cases you will see that you will not be able to find this infinity once you apply the final value theorem, and that's why we don't use this for the case where you have pole outside the z equal to 1 circle. Is it clear?
Okay.
Now in this problem, we need to apply the final value theorem, and this is the x of z. So to calculate it, you have to do the partial not partial fraction, just a fraction of this denominator, and see where are the pole. So when you do that, you will get something like this. So 4z square minus 4z minus 3z plus 3. So you will get 4z z minus 1 minus 3 z minus 1 equal to 0. So 4z minus 3 and z minus 1 equal to 0. So this is the pole. So you see all the pole is either, so one pole is inside the circle and one pole is just at the circle. Okay, so you can apply the final value theorem here. So limit z tending to 1, z upon z minus 1. So in the last slide, I have written it as a 1 minus z inverse, which is same as this one. Okay. Then we have a, wait, sorry. I think in the last slide, I made it one mistake here. It is not this. it will be z minus 1 by z actually, something like this. Yeah, that was the mistake. Now in this case, right, if you put z equal to 1 here, okay, this one coming here. So this expression is essentially the 1 minus z inverse. Okay. Now if you put limit z tending to 1 here, what we will get? You'll get 0. Correct? But we know that from the time expression that it is going to be infinity. Correct? So that's why we don't apply this formula. So limit z tending to 1, z minus 1 divided by z, and then z at z minus 7. Then we have done the fraction of this, so 4z minus 3 and z minus 1. So this will cancel out. And now you can apply the z equal to 1 here. So it will become 8 minus 7 divided by 4 minus 3, which is equal to 1. Okay. So this will be the correct answer. Anyone has any doubt? And the last slide was clear, right? Why we don't apply the final value theorem for the cases where we have the pole outside the z equal to 1 circle.
Sir, could you explain this problem a little bit deeper once more?
Okay, let me just rub this. Okay. So we have the formula which is like this: 1 minus z inverse limit z tending to 1, and you have x of z. Yeah. So okay, so the problem is statement here is that we should not use this formula if pole is outside the z equal to 1 circle. Okay, so if pole is outside the z equal to 1 circle, we will see what happens here. So took the example of xn equal to a to the power n un, where a was greater than 1. Okay, when a is greater than 1, when you take the z transform of this signal, it will be 1 upon 1 minus a z inverse with ROC equal to mod of z greater than a. Also the pole, when you calculate, it will be at z equal to a. Now if you draw this on the z plane, let's say this is the z equal to 1 circle. Okay, this is the 1, this is the minus 1. Now since we know that a is greater than 1, it means that it has to be somewhere here outside the z equal to 1 circle. Now if we take this x of z here and apply here, so limit z tending to 1, and let me just write it in different way. It will be z upon z minus 1 divided by z, okay, this one, multiplied by x of z, which is 1 upon 1 minus a z inverse. Now when you apply the z equal to 1 here, limit z tending to 1, it will become 0, right? Because here we have z minus 1. Once you replace this z with 1, you'll get 0. So based on this formula, we are getting x of infinity equal to 0 for this case. Now let's calculate the x infinity in the time domain for the same signal, a to the power n un. Okay, this is the x of n. I want to calculate x of infinity. I will replace n with infinity, a to the power infinity, u of infinity. Okay, u of infinity will be equal to 1, and a of infinity will depend upon what is the value of a, whether it's greater than 1 or equal to 1 or less than 1. Okay, in this case it is greater than 1, so what will happen that it will become infinity. Okay, so based on this final value theorem we got 0, but based on the time domain signal we are getting infinity. Okay, so because of that, here the reason we are getting the different number is that the pole of this x of z was outside the z equal to 1 circle. Okay. Now if you take the same problem but you make it a less than 0, so in that case x of z will be same here, whatever we have got, but our pole will be inside because a is less than 1. So in the case when a is less than 1, again you have a z equal to 1 circle, but since a is less than 1, your pole will be somewhere here. Okay. Now our pole is inside this circle. Now let's apply the final value theorem. So x of infinity, we will have the same Z transform, right? But only the thing is that a is less than 1. So it will be limit z tending to 1, z minus 1 divided by z, and 1 minus a z inverse. And once you apply the limit, it will become 0. Now let's check the time domain, what is happening. So x of n is a to the power n un, and here a is less than 1. Now let's calculate x of infinity. So a to the power infinity, u of infinity. Now u of infinity will be 1, but a of infinity, a to the power infinity will become 0 because a is less than 1. Okay? So these two are satisfying with each other, right? These two are same. Whether you calculate through final value theorem or calculate it in the time domain, both are same. But for this case, you calculate in the final value theorem, you got the different answer than the what you got in the time domain calculation. So we should have got this answer, but we are getting this answer, and reason is pole is outside the z equal to 1 circle. Is it clear?
Sir, anti-causal sequence, that multiplication factor 1 minus z inverse will remain same, or it's going to be changed
No, for
actually?
anti-causal signal, again, for anti-causal signal also we should not use it, right? Because here I have mentioned we should use only for the causal signal. Okay. So when I derived this here, one assumption was that this is causal signal, and because of that, this term that you see here, x of minus 1 in the derivation, this became 0. And that's why at last you just got x of minus infinity. But if it is an anti-causal, and when you apply x equal to infinity here, what you will get is x of minus 1 and x of infinity both. So it will be something like this, x of infinity minus x of minus 1. Okay, if it is non-causal or anti-causal. So that's why we should not use it for non-causal signal.
Okay, clear, sir.
Now we will go through the inverse Z transform. So again, just like the Laplace transform, we will use a partial fraction and some already known Z transform to calculate the inverse Z transform. So let's say we have a signal which looks like this. Okay, and if you see, it has a multiple zeros, it has multiple poles. Okay, so it has a pole located at z equal to 1, it has pole located at z equal to 1 by 2, and it has pole located at z equal to 2. Okay, and here ROC is given as a mod of z greater than 2. Okay, so first step is to find out what is the partial fraction. So I have already calculated it. So this is the partial fraction. Now again, for this, each of them, we will have two possibilities. One will be the left-sided signal with left-sided ROC, sorry, inside the circle ROC, and other possibility is right-sided signal with ROC outside the circle. Okay, and here we have a ROC in this form. Okay, mod of z greater than 2. Since we have ROC in this form, we will choose the right-sided signal, not the left-sided. Okay. So the inverse Z transform we know for this signal will be this one. So again, I have used this formula, I to the power n un. For this signal, Z transform will be 1 upon 1 minus a Z inverse. Okay. So for this one, this will be the inverse Z transform, and for this one, this will be the inverse Z transform. Okay. So for all three of them, I have chosen the right-sided signal because ROC is in this form. Uh, is it clear to everyone, this problem? Slide. Now this is the second. Again, Z transform is same. I have changed the ROC. Now ROC is in this form. It is kind of stripped between the two circle. One is greater, so it is greater than 1 but less than 2. Okay. So it is greater than 1, less than 2. Now, again, we will do the same partial fraction, and till this point, it is same as what we have seen in the last slide. Okay. After this, when you take the inverse Z transform of each of this term, you need to check for which term you have to check the right-sided and which one you have to take the left-sided. Okay. So for whichever pole is inside the ROC, okay, or you can say before the ROC, for those terms which contain these poles, you should choose the right-sided signal, and for the pole which is on the outside the circle, you should choose the left-sided signal. Okay, so if what I mean is that if you say, let's say that we have this pole 1 by 2, for this particular pole you can say that ROC is outside. Okay, ROC is outward. For this pole also ROC is outward. So this is kind of same as what we have seen in the last slide for the right-sided signal. ROC is outward of the pole, but for this pole ROC is inside, right? So for this, the term which contain this pole, we should take the inverse Z transform, which is left-sided. So the first term is again right-sided. Second term will become left-sided. Okay, this is the term which contain the pole at Z equal to 2, and the third term is again right-sided. Okay, so in this case we have both sided signal because we have right-sided as well as the left-sided. Anyone has any doubt?
So just tell once more that last line.
Okay. So now to find out which one has to be left-sided and which one has to be right-sided, we need to check the pole location with respect to ROC. Okay. So if your pole location is such that ROC is outside, something like this, like outward, for those poles, you should take the right-sided. So we have pole at 1 by 2, and correspondingly we have a term here, this one. And for this one, I will take the right-sided. Now we have this term for which the pole is located at Z equal to 2. Okay. For this one, this is a pole at Z equal to 2. And for this pole, the ROC is kind of inward, not outward. And because of that, we will take the left-sided signal. And for the third one, pole is at Z equal to 1. Again, for this one, ROC is on the outward, and we'll take the right-sided signal.
Okay.
So whenever ROC is outward with respect to pole, you should take the right-sided signal. Whenever ROC is inward with respect to pole, you should take the left-sided signal.
Okay.
Okay. Now, so one way to calculate the inverse Z transform is through that the one that we just saw, which is the partial fraction method. One way is the power series expansion. So here that I was telling about that binomial expression, right? Here, when you have a signal, so I have taken the same Z transform, okay? This one and this one, both are same. But if you check the ROC, they are different, okay? So for this one, this signal is ROC is in the form of mod of Z greater than some number. So it means that it will be right-sided, right? The signal will be right-sided. And for this signal, it will be left-sided. Okay. So when you do this power expansion to find out the x of n, for the right-sided signal, what you have to do is put the denominator in the descending order of the Z. Okay. And similarly, this this one numerator also you should put it in the descending order, okay, not the ascending order, and then do the polynomial division. I hope everyone knows what is a polynomial division. You just take the first term, divide this by this first term, and this is the result 2, and then they take this 2, multiply with this complete thing and put it here, then subtract it. Okay, after the subtraction you'll get this again, divide this 2 Z inverse with this one, you'll get 2 Z inverse itself, and then again multiply it with this complete polynomial and put it here, and then subtract this 2, and it will continue. Okay, so at the top, whatever the result that you'll get, that is the x of Z. Okay, x of z expansion you can say. And in the x of z expansion, you will see that it is decreasing order of the z. Okay, z to the power is going down. And that is the sign that it is a right-sided signal. Okay. And if you are getting ascending order of the z, it means that you are doing it wrong. Okay, you are doing it in this way then. Okay, so you have to be careful how to arrange the this polynomial when you are calculating this power series expansion. Okay, in this case you will be arranging in this way. Okay. It is now ascending order of the z. Lowest will be on the left, highest will be on the right. Okay. So highest here is 0, lowest is -1. So you have arranged in this way. Again, you'll do the polynomial division here. And after the polynomial division, you'll get the x of z. Okay. Now after finding the x of z, you can calculate the x of n. So first term doesn't have the any z multiplication. It means that it corresponds to n equal to 0. Second one has z to the power -1. This corresponds to n equal to 1. This corresponds to n equal to 2, n equal to 3, and so on. For the second example, -2 doesn't have any power of z, that corresponds to n equal to 0. This corresponds to n equal to -1, n equal to -2, n equal to -3, and so on. Okay. So does this clear the doubt? I think someone has asked few slides back. Okay, then let me go to the next slide. Now let's say that we have a problem where we have been asked to find out the x of n, and this is the x of z. Okay, and for this particular x of z, we don't know the inverse inverse z transform already known. Okay, this looks very different than what till now whatever signal we have seen. So what we have to do is to expand it, and then we can calculate the x of n. So we know that e to the power x is equal to 1 plus x square by factorial 2, x cubed by factorial 3, and so on. So similarly, e to the power z square, you just need to replace x with z, so it will become 1 plus z square z to the power 4 factorial 2, z to the power 6 factorial 3, z to the power 8 factorial 4, and so on. Okay. Now based on the power, you can calculate what is the x of n. So x of n is something like this. So for n equal to 0, it is 1. For n equal to -2, it is 1. N equal to -4, it is 1 by root 2, and so on. Okay. So this is how we can find out the x of n for this x of z. Okay. Similarly, I have put one more problem. This guy you guys can solve. So here you have a cos 2z inverse, and for this case we need to find out what is the x of n. So you can expand the cos. You can put uh, the I think you guys might know this. Cos x is equal to 1 minus x square by factorial 2 plus x to the power 4 by factorial 4 minus x to the power 6 by factorial 6, and it continues. Okay, this is the expansion of the cos of x. You can use this expansion and find out what is the expansion of x of z, and from there you can find out what is the x of n. Okay. So for this kind of problem, wherever whether it's a log of some z, or cos of some z, or sine of some z, or exponential to the power some z, in that case you can expand it, and then from based on the power you can calculate the x of n. Okay. Anyone has any doubt in this?
In that problem, a raised to z square,
Yeah.
after 1 plus z square plus z raised to 4 by and so on. So that next step, I just need a little more clarity on that.
Oh, which one? This
This one,
this
yes.
z to the power 6. No, this one what we did is we just put
Instead of that,
just replace
it
this
is
x with z square.
z
So
square.
yeah.
And after that, the solution.
Okay, it will continue. It will expand like that. So there will be z to the power 10 factorial 5, z to the power 12 factorial 5, and so on.
No, sir. No, sir. After that, our solution like x of n.
So no. So the problem will be something like this. Find the x of 3 or find the what is x of 4. Okay. We don't need to find complete x of n. We need to just find out how does it looks like, and then from there we can find out what is x of 3 or x of 4 or x of -2 or x of -4 and so on. Okay. So in this case, once you find out this expansion, you can tell that x of 3 is equal to 0 and x of 4 is also equal to 0. Okay, because all the positive value of n, we don't have any expansion here, right? For positive value of n, we should get negative power of z. Okay. So the question will be like this, like you have to find out some like x of 3 and 4, and for this case, like if x of n is given, it will be like kind of piecewise breaked. So it will be written as for n greater than 0, it will be equal to 0, and then for n equal to less than 0 and odd, again it will be 0, and for n less than 0 but even, it will be given as something like this. So you can write it like 1 by mod of n by 2, something like this, right? 1 by factorial mod of n by 2. Okay, so for example, this correspond to wait, not by 2, it will be multiplication. Factorial 2 into mod of n, actually. Is it 2? Wait, no, I'm doing a mistake here. Yeah, it is indeed n by 2, not into 2. Factorial mod of n by 2. Yeah. So if question is asked for this, like find out what is x of n, it will be kind of piecewise break here like this. Okay. So for n less than n greater than 0, it is 0. For n less than 0 and odd, it is 0. And for n less than 0 and even, it is like this. So if you put, let's say, n equal to let's say if you put n equal to -2 here. Okay. So when you put n equal to 2 -2, you'll get 1. When you put n equal to -4 here, you'll get 1 by factorial 2. When you put n equal to -6 here, you'll get 1 by factorial 3 and so on. Is it clear now? So in this kind of question, if this is not asked, if this is asked, this will be in the piecewise break function, not like some continuous like one just expression. It will be like multiple expression here. Similarly for this cos x also, if you try to write x of n, there will be like multiple piecewise break function. Then let me go to the next slide. These are some of the already like non-Z transform. I put it here. This is useful if you remember it, because to calculate it in exam again it will take time. So it's better to remember again this few of this Z transform. Okay. Now next is the transfer function. So we are going to use the convolution property here that we saw a few slides back. So if you have a system with impulse response h of n, input x of n, then output y of n will be given as the convolution of the x of n with h of n. Okay. Now when you take this complete thing in z domain, so what will happen that, so this x of n will become x of z, h of n will become h of z, and y of n will become y of z, and y of z will be equal to x of z into h of z, or you can write h of z is equal to y of z divided by x of z. Okay, so this since it is changing from convolution to multiplication, it is much easier to calculate sum of this thing in the z domain. Okay. So let's see if you
So can I see the last slide once more? That before that, just
okay, this one. Okay.
just take note. Okay, thank you, sir. I took it.
Now, some of the problem in the exam can be something like the difference equation. Okay, so in the Laplace case, in the continuous time case, we had the differential equation to represent the system. In the case of discrete time, it will be the difference equation. So you have this difference, it can be something like this kind of difference. I've just taken one of the examples, but it can be in any other form also. So if this difference equation is given, and if you are asked to find out what is the h of z or what is the h of n, then you need to take the help of the z transform here. Okay. So for example, let's say we have been given this input output relationship in terms of this difference equation, and we were asked to find out what is h of n. So you have to take the z transform on the both side of this difference equation. So y of n will become y of z, y of n minus 1 will become y of z, z inverse, y of n minus 2, y of z, z power minus 2. So I'm using the time shifting property here, and x of n will become x of z, and x of n minus 1, x of z, z inverse. Okay. Now on the left side, you can take the y of z common, and the right side, you can take the x of z common and calculate the y of z divided by x of z. That will be the h of z. Okay. So I've directly written it here. Now here, for the denominator, you can do the fraction here. You'll get this, and after that, find the partial fraction. Next step is to find the partial fraction of this, and once you have the partial fraction, you can take the inverse z transform, and that will give you the h of n. Now there is a just opposite way to give the problem. So in the opposite way is that you have been given the h of z, and you need to find out what is the difference equation. Okay. So in that case, so this is, let's say this is h of z, and it is given in this formula. So you can write it as a y of z and x of z, and then you do this multiplication that x of z is x of z multiplied by 5z plus 2 is equal to y of z, z square plus 3z plus 2. Okay, and then apply the property of the time shifting. Okay, so this x of z multiplied by 5z will become x of 5 into x of n plus 1. Okay, 2 into x of z will simply be 2 into x of n in the time domain. And similarly, on the right hand side, you can write it as a y n plus 2 plus 3 y n plus 1 plus 2 into y of n. Okay, so this is the expression that you will get. But if you see this expression and this expression, they don't look same. The reason is that here you can replace this complete thing with some different n. So you can replace n with, let's say, n minus 2, okay, or n minus 3 kind of number on both left and right side. The equation will still be the same. It will still be the valid. Okay, so when you take this 5x n plus 1 and replace this n with n minus 2, what will happen? That this will become 5 x of n minus 1 plus 2 into x of n will become n minus 2, and this will become y of n plus 3 into y n minus 1 plus 2 into y. Now if you see, both of them are same. Okay, this and this are same. So when you do this replacement of n with n minus 2 on both left and right, it doesn't affect the system. Okay, it doesn't affect the characteristic of the system. System is still the same. So if you take this and find out the h of z, and if you take this the blue one and find out the h of z, both will give you the same h of z. Okay, there will not be any difference. Go to the next slide. Now, a unit step response of the system is described by this difference equation. Okay? And so we need to find out if this is the difference equation, what will be the unit step of the system. So system is given in difference equation. Input is given as a unit step. We need to find out for this unit step what will be the output. And output we need to find out in Z domain itself. We don't need to convert into the N domain. So first, we know that output y of z is given as h of z into x of z. Okay, h of z we can find out with this difference equation, and input is given as a unit step. That means that x of z is z upon z minus 1. Okay, this is already we know. Now h of z you can calculate. So take this system equation and take the z transform on both sides. So it will become y of z plus y of z, z inverse is equal to x of z. Okay, or you can also write as a y of z, yx of z is equal to 1 upon 1 plus z inverse. Okay, now this one you can also write it as z upon z plus 1. Okay, so let's replace this z upon z plus 1 into z upon z minus 1, or you can write it as z square divided by z plus 1 z minus 1. So this will be the correct answer. Let me go to the next slide. Now we will see the system in the Z domain and see whether how to find out whether system is causal or non-causal. So this we will do the similarly what we have done for the Laplace domain. Okay. So we know that in the if the impulse response is given, system will be causal if h of n is 0 for n less than 0. Okay. So again, here the result is very similar to what we have seen in the Laplace. So in this case, if ROC is in this form, mod of z less than some number, then signal will be left-sided, right? It will be left-sided. And once the signal is left-sided, when you plot it, you are going to get the signal for the negative value of time also. And that means that this signal will definitely be a non-causal system. Okay, so whenever the ROC is in this form, the system is always a non-causal. Okay. Now when ROC is either this form, okay, in that case system may or may not be causal. Okay, it depends on where the signal is starting. So when the ROC is in this form, we know that the signal will be right-sided. Okay, but right-sided doesn't guarantee that it will be causal, because right-sided can start from this point also and go like this. Okay, so it can start before the n equal to 0 and it can start after the n equal to 0, both. So for if the ROC is in this form, it may or may not be the causal system. Okay. Third case is when mod of z is greater than some number and less than some other number. In that case, it is definitely non-causal. Okay. Okay. So here we can conclude that if mod of z less than some number, non-causal, mod of z greater than a less than some other number, again non-causal, mod of z greater than some number, it may or may not be causal. Now, whenever it is mod of z greater than a kind of ROC, when you check the x of z, okay, and when you expand this, and if you get the positive power of z, you can conclude that it will be non-causal. Okay, because once you get the positive power of z in the x of z after the expansion, it means that it has some value at the negative time. But if doesn't have the positive power of the z, it means that it will be the causal. Okay, now to find out whether we have the after the expanding this, whether you get the positive power z or not, you need to just do one thing. You just check the numerator polynomial and denominator polynomial and see whether numerator polynomial is higher than the denominator polynomial. Okay, so if numerator polynomial is higher than the denominator polynomial, it will be non-causal, because after the division of the denominator with the numerator, you'll definitely get the positive power of z. Okay, but if numerator polynomial is same as denominator or less than the denominator, in that case system will be causal, because in that case you will not get the positive power of the z. Okay, so with the help of the ROC, you can conclude whether system is causal or not. Anyone has any doubt? Okay, let me go to next slide then. Next is the stable system. So from the h of n or the impulse response, we know that system will be stable if it is satisfying this criteria. Okay, now let's take this h of z, which is the z transform of the h of n, and let's take the mod of it. So once you take the mod of it, okay, I am applying some inequality that here inequality is on outside the summation sign, here inequality is inside. So once you do that, this will also be always be greater than this one. And so once you apply this inequality on individual term here, again this term will be more than this one. Okay, now this z to the power minus n, let me replace this z with equal to 1. Okay, once I replace this z equal to 1 or mod of z is equal to 1, this will be same as this expression at the top. Okay, and if this is converging, then definitely h of z will also converge. Okay, so if the system is stable, we know that this is going to be a finite number. In that case, this is also going to be a finite number for z equal to 1. Okay, so for the stable system, h of z will be finite for z is equal to 1. Okay, and since h of z is a finite for z equal to 1, it means that z is equal to 1 is a part of the ROC. Then only that's why for h of for this z equal to 1, we are getting h of z as a some finite number. So if any system is a stable system, its ROC should contain this z equal to 1 circle. Okay, if ROC is containing the z equal to 1 circle, then the system will be stable. And if it is not containing the z equal to 1 circle, it will be unstable. Now, if you can correlate this with the Laplace, in the Laplace, it was j omega axis. It should contain the j omega axis, then only it will be stable, otherwise not. In this case, it should contain the z equal to 1 circle, then only system will be stable, otherwise not. Anyone has any doubt here? Let me go to the next slide. Next is about the, let's say we already know that system is causal. Let's say then what is the criteria for the stability? We'll just slightly simplify that. So first thing is, we are assuming the system is already causal. And since system is already causal, its ROC will be something like this. You draw a circle and ROC will be outside this. ROC will always be in this form, okay, for the causal system. Now let's say this is a causal and we want that what is the criteria on the stability, okay. Now we know that for the system to be stable, ROC should contain the Z equal to 1 circle, okay. So let's say this is Z equal to 1 circle. So let's say this is A and this is 1, okay. So our ROC is in this form, okay, and this is the Z equal to 1 circle. So it means that A is less than 1, okay. So if system is a causal system, then it will be stable only if the ROC is containing the Z equal to 1 circle, that we know. Now there is another way to write this thing, and what is that? That is, we know that this A is the point of the highest pole, okay, or you can say that A is the point which represents the highest magnitude pole, okay. Now if we have a system where all the pole is inside the Z equal to 1 circle, then definitely when you plot the ROC, it will start from that pole and go towards the infinity. And in that case, it will contain the Z equal to 1 circle. Okay. So I will take the two scenario. First scenario is that all pole inside the circle, inside Z equal to 1 circle. Okay. So if all the pole is inside the Z equal to 1 circle, and let's say the maximum pole that we are getting is A, okay. So it means that ROC will be in this form, and in that case it will contain the Z equal to 1 circle, okay, because A is less than 1, because all the pole is inside the Z equal to 1 circle. Now second case is when, let's say we have a causal system and its maximum pole is, let's say, BE. So it means that ROC will be in this form, mod of Z greater than B, okay, and let's assume that B is greater than 1. Okay. So what it means is that we have at least one pole which is whose magnitude is more than 1. In that case, let me plot the Z equal to 1 circle. This is the Z equal to 1 circle, and here B is less than 1. Now if you see this is the ROC outside of this Z equal to B circle, and this ROC doesn't contain the Z equal to 1 circle. Okay. On the other hand, on the right side, when our pole was inside the Z equal to 1 circle, it was containing the Z equal to 1 circle. Okay. So here what I mean is that whenever the system is causal, it will be stable if all the pole is inside the Z equal to 1 circle. Okay. If that criteria is satisfied, then we can say that the system will be stable. Okay. So in summary, I can say that for causal system, if system is causal, then to be stable, all pole should be inside the Z equal to 1 circle. Anyone has any doubt? Okay, let me go to the next slide then. This is the last problem and then we will stop here. So here we have a two discrete time system H1n and H2n. Okay, H2n is not written here. So there is a two discrete time system H1n and H2n, and their impulse response are given as a delta n minus 3 and delta n minus 5, and these two systems are cascaded, then what will be the overall response of the system? So in the last class, we have discussed about the cascaded system. So whenever we have a cascaded system, the effective impulse response or the overall impulse response will be the convolution of these two. Okay. Now in this case, I'm talking about the discrete time system. Here also, when we try to find out the effective impulse response, h of n, it will be the convolution of the h1n with h2n. Okay. So in this case, we need to do the convolution of del n minus 3 with h2n. I am not writing h2n as a delta n minus 5. I will write it shortly. So we know that whenever you have a signal delta n minus a getting convolved with x of n, the resultant is x of n minus a. Okay. So you can think of this h2n as x of n and delta n minus a with delta n minus 3. So your resultant will be h2n minus 3. Okay. And what is h2n? H2n is delta n minus 5. So you can write it as a delta n minus 5 minus 3. So which is equal to delta n minus 8. So it means that this will be the answer. Now here, if you are confused here about this property, you can solve this problem in the Z domain also. Okay. Since this is a convolution here, in the Z domain it will be multiplication. So it will become h of z equal to h1z and h2z. Okay. Now what is the h1z? So this is delta n minus 3. So h1z will be z to the power minus 3 and h2z will be z to the power minus 5. So effectively it is z to the power minus 8. When you take the inverse, it will be delta n minus 8. Anyone has any doubt?
So I understood about the Z domain, but the time domain, just please do explain once more.
Okay. You remember this property, right? This delta n minus a convolution with x of n equal to x of n minus a. Okay. So essentially we are using this property here. So here this x of n, you can think of this as a h2n. Okay, this is same, this two are, let's say. And this delta n minus 3 is same as delta n minus a. So it means that a is equal to 3 here. So here when you replace this x of n with h2 of n and a with 3, this one you can write it as a h2 n minus 3. Okay. Now we know that what is the h2n? So h2n is equal to delta n minus 5. Now I want to calculate what is the h2n minus 3. So I need to replace this n with n minus 3. So on the right side also I will replace n with n minus 3, and there is already minus 5. So it will become delta n minus 8.
Okay. Got it.
Anyone has any other doubt? You can ask any topic that we discussed today, any slide.